Hey everybody, welcome back to Module 6 in multi-level modeling. This week we get to talk about three-level models. So now we've sort of gone past the basics, what I call kind of the nuts and bolts of multi-level modeling, and we've kind of taken that step by step. So now we're going to get into some interesting kind of advanced topics that may be useful to you down the road, or maybe even now, depending on what type of data you have. So let me share my screen. And then I'm going to pop over to the slides, and you have a link to these slides available on Canvas as well. So just a couple questions I wanted to address from last week. So a lot of folks asked a similar question. When it comes to assessing model fit, we talked about model fit and effect size last week. There are a lot of different choices, right? You can look at AIC, you can look at BIC, you can do a likelihood ratio test or an LRT, and sometimes you get conflicting evidence. And I think, if I'm remembering correctly, on the content review for this week, you got sort of conflicting evidence. AIC said one thing, BIC said something else, the LRT said something else. So what do you trust? What statistic do you go with? So my personal preference is to go first with BIC. Is that personal preference? Yes, it is personal preference. You could get different answers. But, and Garson talks about this a little bit in his coverage of BIC. BIC is the most consistent measure of model fit across different types of models, across large and small samples, different model specifications. BIC tends to be really, really consistent. And so for that reason, if you can only trust one measure, I would go with that one. So if you're in a pickle, BIC is probably the best bet to go with. Okay, so now we're going to get into three-level models this week. Very exciting. We're going to add a level here. So last week we learned how to use some goodness of fit statistics and also to estimate effect size for two-level, multi-level models. So we basically learned how to sort of solidify things that we've already been talking about for a while, and then talked about assessing effect size using measures like the WGPRV and the BGPRV, as well as the multi-level R-squared. So now we're going to add a third level to our models. And believe it or not, they seem kind of complicated, but they're actually fairly common in social science. So here are just a couple examples of what a three-level hierarchical linear model or multi-level model might look like. So if you are studying employees, those employees are probably nested within some smaller organization in their workplace, like a unit or a department. And that department is probably in turn nested within a larger organization or company. So that could be potentially, if you survey a bunch of different organizations, you could have a three-level problem there. You could have employees that are nested within departments, which are in turn nested within organizations. Patients, of course, are nested within doctors, and that's an important nesting to account for, but doctors are typically also nested within hospitals or clinics. And so you have another layer there on top of that, which captures another layer of complexity. Students, of course, are nested within classrooms, but of course, the classroom is the most proximal environment that the child is in, but you're also nested within schools. You could also be nested within neighborhoods. We'll talk about what's called cross-nesting or cross-classified nesting a little bit later in the semester. But for now, we'll just think about this example where one student is in a classroom, that classroom is nested within schools. And of course, if you sample lots of different schools, then you have a bunch of data that actually has three levels of nesting instead of two. You also could have students nested within schools, nested within districts. So maybe you don't know necessarily what classroom a student is a part of, or maybe, for example, a student, let's say, is in middle school or high school where they're not in the same classroom all the time. So the school might be the most relevant nesting characteristic. And those schools are nested within districts or divisions, I guess is the Virginia term, school divisions. Another example, this one's kind of wild. So you can have repeated measures or longitudinal data nested within one student, and that student is nested within a classroom or a school. So here, if we're throwing you for a little bit of a loop. So before we were just, up until now, we've only studied cross-sectional multi-level models. So we've only talked about one student measured at one time point nested within a particular context. But as we will learn next week, multi-level models are really good at handling longitudinal data. And so you can actually have repeated measures nested within a student, nested within their context. And that's a really nice three-level model. So lots of different options for a three-level model, lots of ways in which you can kind of see complexity being represented in more than two levels. And of course, in all cases, and this is very important to remember, just as it is with two-level models, your outcome, your dependent variable, is measured at level 1. So no matter what sort of complicated nesting scheme you come up with, your outcome has to be measured at the bottom. So if you have, for example, students nested within classrooms, nested within schools, but your outcome that you're interested in studying only exists at the classroom level, that's probably not a three-level problem. That's probably a two-level problem. That's probably a classroom nested in school question as opposed to a three-level problem. And since we're talking about levels, Great British Baking Show or Great British Bake Off, depending on whether you watch it in the UK or not, one of my favorite shows. Whenever I think of levels, I think of cake and the really cool cakes that they make on that show. And here is Kate's 3-level sticky toffee apple caramel cake, which I would love to try and make sometime. It's really fun. So yeah, I don't know about you, but whenever I think of MLM, I just think of some delicious cake. Okay, so Garson, as usual, has a nice diagram, and this comes from chapter 8, which is the assigned reading for this week in Garson. So you can, just as in a two-level model, you can represent a three-level model with a similar diagram. So here we have a null model, essentially, or I guess it's not quite a null model because we have this measure of year, but this is a situation where we have repeated measurements nested within a particular child, nested within a school. And so our outcome here is math, and we have multiple years of measurements nested within the same child. So here, year is the indicator that tells you which year of scores you have. So let's say we have the child's math score from 2015, 16, and 17. So in that case, we would have 3 years nested within each child. And the child ID is actually our level 2 variable. So that's a little bit different, right? Before it was the classroom or the school, but now in this case, if we have repeated data, the child can actually be the nesting data in the cluster. And then we have a higher level cluster here, which is school ID. So this can be thought of as a 3-level unconditional random intercept model. So 3 levels, 1, 2, 3. Unconditional meaning we don't have any other covariates. Random intercept model, meaning we are only accounting for school ID and child ID in the intercept. And then with longitudinal measures. So we have repeated measures by student. So again, that diagram might be helpful in kind of picking apart the different possibilities. So here's a typical scenario. You may begin by analyzing a model, a data set using a 2-level model. And then you realize, wait a minute, those level 2 units are also clustered. Just like in a 2-level model, when you ignore level 2, that's a problem, right? So when you are treating something as a regular 1-level regression, when there actually is this clustering variable at level 2, that can cause problems. The same issue happens with a 3-level model. If you have a 2-level model with a 3rd level that's being ignored, you can have issues with the independence assumption. You can get weird residuals, biased estimates, all those things. And so the nice part is it's pretty easy to introduce another level of clustering. So this could be this example, each one of these little circles is a student, and each one of these medium-sized circles is a classroom. So students nested within classrooms, and those classrooms are in turn nested within schools. So we're accounting for variability at all these levels. We're accounting for student level variability, for classroom level variability, and school variability. And we can actually introduce predictors as well. Now, one thing to think about, we assume for this kind of model that the nesting is what's called hierarchical. Now, what does that mean? That means that if we call this little dot down here student A, we assume that student A is only in this classroom, and this classroom is only in this school. And that's called hierarchical nesting. It means that each unit is only a part of one other unit. There's no cross-level or cross-unit connections. Now, this might be realistic, for example, in an elementary school, where a student spends most to all of their day in one classroom. But if you're looking at perhaps a middle school or a high school, this gets much trickier because this student might be in this classroom, this might be their biology class, but this might be their algebra class, and this might be their world geography class. And so you have to come up with a fancier model to account for that. And that's what's called a cross-classified model. And we will cover that all the way at the end in Module 11. Module 11. So one question to ask yourself is the nesting hierarchical? Is the nesting that I'm looking at hierarchical, or do I have cross-level connections between the units? Okay, so we're going to talk just a little bit about the notation. So this is a refresher of the notation for a two-level null model. So a two-level null model. So a couple things to notice. We have an ij subscript here because we're looking at two levels. Student I, for example, nested within classroom J. So you'll see those I's and J's follow through in the notation. Student I in school J. We have betas for the level 1 slopes. So beta 0 is here, and beta 0 is represented as an overall, what we call a grand mean, which is gamma 0, 0, and then mu 0j, which is a random effect at the school level. And then, of course, at level 1, we also have an individual level term, which is epsilon ij. And we have our distribution of the random effects down here. We only have two random effects in a two-level null model. We have a random effect at level 2, a random intercept, and we have a random effect at level 1. Okay, so essentially the predicted score for a given student is now, if we look at this reduced form equation, it's now equal to some overall mean, that's your intercept, plus some random variation at the school level, if it's students nested within schools, plus some random variation at the individual level. So that's a two-level model. Now we're going to kick it up a notch, and we're going to look at three-level models. Okay, three-level models. Now notice we now have a subscript that is ijk instead of just ij, because we have three levels. That means we have three nested things that we're looking at. It might be student nested within classroom, nested within school. Let's go with that. So I is student I, nested in school J. Let's do school and division, that's what I put. Nested in division K. So we have three levels of nesting. And now we have pies. So the bottom level here is represented by a pie. And those pies then are represented as betas at level 2, and those betas are represented as gammas at level 3. So essentially we create a new notation for the very bottom level, and those are pies. So pies, those estimates of the slopes and intercepts are pies, and then we have betas, and then we have gammas, just like we had before. So now everything has basically moved up a level. And now we have a new level 3 random effect. So notice epsilon ijk now, since we have a 3-level model, is the level 1 random effect, the student level random effect. Mu 0jk is the school level random effect, if we're looking at school J. And mu 00k is the division level random effect. So now we have 3 random effects here. We have an individual, a school, and a district level random effect. So in other words, the predicted score for a given person here now is gamma 000, and that is an overall average plus random deviation at the division level plus random deviation at the school level plus random deviation at the individual level. Pretty wild, huh? Pretty interesting. And then, of course, our residual distributions, we now have another random effect. So we still have our level 1 random effect, which is epsilon ijk. And these are all assumed to be normally distributed with a mean of 0 and a known variance. The known variance at level 1 is sigma squared still. And then mu 0jk is your random variation at the school level, so that's level 2. And its known variance is tau 00 with a little 2 next to it. So the level 2 tau. And then we have a level 3 random variance, which is u00k, and that is, its variability is represented by tau 003. So we have 3 random things we need to pay attention to now instead of just 2. A little bit tricky. Likewise, we also now have 2 ICCs instead of 1. So if you recall the formula before for calculating an ICC in a 2-level model, it was equal to tau 00, which is the variability at level 2, divided by the sum of the level 1 and level 2 variability added together. So with the 3-level model, it gets more complicated because you have 3 components instead of 2. So you actually have an ICC at level 2 and an ICC at level 3. The ICC at level 2 is the level 2 variance divided by the sum of all 3 variances. And likewise, the level 3 variance is equal to, the level 3 ICC is equal to the level 3 variance divided by the sum of all 3 variances. So now you actually report 2 ICCs. So you'll have variability at level 2 and you'll have variability at level 3. Kind of wild. Okay, so a little bit about today's data. There's a nice, you'll notice this is a hyperlink to a really nice article that describes the study from which the data that we're collecting are from, and it's called Project STAR. You may or may not have heard about this. Another word for Project STAR was the Tennessee Class Size Study. And this was a really unique, rare, and interesting study that was conducted in the mid to late 80s and early 90s in the state of Tennessee. And it's among the largest, most expensive, and famous educational experiments that has ever been conducted in the US. It was a really interesting study that produced data that people have been studying for almost 30 years now. There are still questions that are being answered with the Project STAR data, which is pretty cool. So what happened was the state of Tennessee actually approved and funded this study to the tune of millions of dollars. So the state actually approved a large-scale randomized controlled trial to see the impact of class size, which was wild. And all public schools in the state were invited to participate. Now, not all of them did participate, but many, many, many did. And what they did was they looked at students who were in grades K2, and they actually randomized students to classrooms. And so students were randomized to one of 3 conditions. They were assigned to a small class, a regular class, and a regular class with an aide. So this is really rare. Often it's extremely hard to get random assignment to classrooms because there are so many factors that determine what classroom your child might end up in. But in this case, they had to get cooperation. As schools that wanted to participate, they got some extra funding to be able to do this. They had to agree to the randomization. And so they were able to successfully pull this study off. It's interesting. A lot of people would say probably 12 to 16 isn't a super small class, especially for kindergarten. But that was what was considered small. And then, of course, regular was 16 to 28. And then there was this regular condition with the aid. A ton of stuff was measured: math, reading, student motivation, you name it. And it's all available in the data set that we're working with today. This actually would be a great data set to use for your paper, your final paper, if you were interested. You could try lots of different things. But the most important question that was asked, well, at least according to the people who funded the study, was, does class size matter? So essentially, is it worth it to pay more money for smaller classes, and does it improve outcomes for younger kids? And there actually was a high school version of this that also was carried out at the same time on a smaller scale, because people wanted to know, do you get the same benefit from this kind of a project at the high school level compared to the pre-K or K2 level? So really cool, study. The data are available. I believe I got this from Harvard's data archive. It's online, freely available. There's a really big code book that has a bunch of information about it too. We're just using a little slice of the data. It's longitudinal and is really complex, but we're using just one little part of it. Okay, so the last thing I'll point out before I let you go is that I again have annotated output for the 3-level null model and the 3-level model with predictors. And I do that in both Stata and in R. So if you're wondering, again, I know interpretation is tricky and takes time and practice. So if you want to refresh your memory on what am I looking at in this output, I have examples here. So here's the example in Stata of what everything looks like. I also talk about it in the video. So I pull apart the different elements in the video. And I also have a similar model here with predictors. So I've actually added predictors to the model, to the 3-level model. And with Project STAR, it is students nested within classrooms, nested within schools. And the school, actually the class type, was assigned at the classroom level. So you had some classrooms in the same school. Some of them were big, some of them were regular, some of them were small, some of them had a teacher's aide. And so class type was actually a level 2 or classroom level predictor. So I've got the interpretations there. And the same thing here in R. I've got all the elements spelled out for you. It looks very similar. The estimates, again, as is typical, don't differ very much at all between Stata and R. And there are the results there. So I think that's all I've got on 3-level models. The demonstration videos will go into more detail about how to run things and interpret them. But hopefully that's an overview. Just to recap, we basically are extending everything we learned one notch this week, and we're talking about how to estimate 3-level models. So we talked briefly conceptually about what a 3-level model is and some practical examples from medicine, education, social sciences. And then we talked about what that means in terms of the math behind it. We looked at the notation. We've essentially added an additional random effect that we then have to account for in our models. But otherwise, the estimation of these things is pretty stable and pretty similar to what we studied before. So hopefully that's just another tool you can add to your toolkit. All right, I think that's all I've got. Good luck and take care.